Hello everyone. Today I'm excited to introduce VGGSounder, a large-scale audio-video benchmark purposely built for evaluating foundation and embedding models. This work is a joint work between Technical University of Munich and University of Tübingen. So let's start with a couple of the research questions. When one worked with the multimodal models, he will eventually ask himself, do they treat the modalities balanced, independently, or do they over-rely on one modality? And what about cases when the target classes exist only in one modality and doesn't exist in another class, in another modality? After all, no one wants a system that can detect something only when it both sees and hears it. And unfortunately, most of the existing benchmarks by design aim to have a high modality correspondence. And that makes their accuracy not really useful in order to understand how the modality is used. Let's look at the example.
数的，漂亮。
This video contains 4 different classes. First one, playing table tennis. We can both hear and see it. But there are 3 other classes: crowd, people clapping, and male speech. Those classes we can only hear. And in order to fix this issue, we built a VGGSounder, a large-scale video tagging benchmark containing more than 15,000 clips across 309 diverse classes. Each clip is labeled by human annotators for reliability, and crucially, we provide a modality-specific tags. So to say, for every class, we state whether the evidence appears in the audio, video, or both. To our knowledge, VGGSounder is one of the first publicly available benchmark with a complete per-modality annotation for every class. Here are example samples from VGGSounder benchmark. Each video contains multiple classes, and they might be only audible, only visible, or both. Such modality annotation opens up doors to a new analysis of multimodal models' behavior. By having such annotations, one can benchmark their model only within the classes available in one modality, for example, audio video, or in contrast, evaluate the model only in the subsections where the audio and video correspondence is guaranteed by several human annotators. On top of that, we label 3 additional meta classes that characterize the video input: background music, voiceover, and a static image. Such annotations allow us to analyze how the model balances modalities when making predictions. To be precise, we introduce a new metric, modality confusion. It measures a fraction of a dataset that model classified correctly using a single modality, but misclassified when both modalities were used. It captures how one modality affects predictions of another and highlights the model over-reliance on one specific modality. As one can see on the right, all of the models that we benchmarked, both embedding models and open source and closed source foundation models, they have from 4 to 11% of the samples where the model fails to classify samples correctly with 2 modality inputs, while successfully predicting necessary classes when only one modality were provided. That shows that even the strongest foundation models, such as Gemini family, cannot fuse modality perfectly. Our benchmark uses 3 different protocols. First one is accuracy, zero-shot or GPT-assisted evaluation based on the model, F1 score, and the real accuracy introduced and overdone with ImageNet. All of them allow us to benchmark large language models more fair than the previous datasets. Here on the right, you can see that, for example, Gemini 1.5 Flash performs more in audio than it was measured before. So to say, we can claim that VGGSound was under-evaluating the audio modality, while the VGGSounder captures the performance of the model and audio modality better. There are other interesting findings that we have. For example, across all the models, we can see that the purpose-built embedding models such as Kavami and AVCM perform comparably to both open source and closed source, suggesting that foundation models have reached and some modalities even exceeded the performance of specialized models. Another finding is that the embedding models fine-tuned on VGGSound generally have stronger unimodal performance with the audio inputs compared to the visual inputs. However, interestingly, this trend is reversed for majority of foundation models, which seems to be biased towards video input, while with the unimodal video performance being substantially higher than the unimodal audio performance. So you probably wonder, how did we build this dataset, right? So we started with a widely adopted, recognized in community VGGSound dataset. Then we identified and fixed several issues with VGGSounder, such as co-occurring classes, overlapping classes, modality misalignment, and then we run two independent pipelines in Amazon mTurk. One that adds modalities to pre-existing VGGSound labels, and the second one that extends them with the new classes. The final labels were merged with use of David-Skin algorithm, and that resulted us in a new comprehensive benchmark with extra 17,000 new labels and almost 33,000 modality annotation, and we just spent more than 6,000 human hours. Thank you very much for watching it, and check out our product page.